All right, we're back. We are Game 2005. That's Game Physics here at George Brown College, and it's the fall 2017 semester. And we are week 10. I'm shaking my head. I don't know, kind of week 10. Equivalent, part one of our broadcast. We're talking today about energy of a system. Okay, when we talk physics, this is one of the areas that people have trouble with because again, I mean, all areas of physics it can be challenging because you have to kind of understand what's going on. And this is more complex than others because it includes some of the stuff we did before. It assumes that you know. See, when we make assumptions, things are bad, right? It assumes that you know what we did before and understand it well. And then we introduce new stuff today. Okay, but before we get into it, I want to talk about next week a little bit, okay, just from a scheduling perspective. I want to remind you that on Tuesday and Thursday of next week, we will be hosting our test number 2 during lab time. Okay, so next week, Tuesday and Thursday, lab time, we're going to be hosting our test. Okay. Also, to remind you that next Friday, that's the 15th, right? We will be, that's when your assignment 2 is due. So test 2 and assignment 2. All next week, right? So if you haven't had a chance to start, who started? Who started so far? I got one person? 2 people? You guys are killing me. I know there's other stuff going on, but you got to start this stuff, guys. There's only 3 questions, and I'm allowing like 3 people to work together or whatever. I know there's a lot going on, but if you don't start, it's gonna really, huh? What, this Thursday? Yeah. All right. Hopefully this Thursday you guys will be, a little better off. Please don't wait too long for this. I mean, it's not like it's long. It's just that, you want to get practicing so that when your test comes around next week, you're good. Like, you have an idea of what to do. On Tuesday during lecture time, okay, so Tuesday and Thursday during lab time, we have our test. Tuesday during lecture time, there will not be a regular lecture in terms of I'm not going to be introducing new material. I will be reviewing older material because that day is your test, okay? So it's kind of a weird thing. It would have been nice to have, another day separating your test from the review, but there isn't time for that. Also on Tuesday, I will be sharing the cheat sheet with you electronically, right? So I might be able to do it earlier actually, but I want to be able to share the thing electronically so you can add things to it. I'm not going to do it like last time where I printed it out and gave it to you. This way I'll just give it to you. You add stuff to it. As long as it's yours, please don't pass your cheat sheet along because I'm going to ask for it. So you can print your own cheat sheet. I will probably have some because some people are going to forget to have a cheat sheet altogether because that's the way people are. They don't produce a cheat sheet. They expect me to produce it for you. Right? I'll produce it anyway. I'll have some, some stuff on there that I recommend that you have, and I'll print some out for the test just in case you forget. But you can add to it, and that means as long as you keep it on, one page double-sided, so the cheat sheet that I give you plus something on the back, or if you want to add to the front or whatever, it's totally good. But I don't want you to make a cheat sheet for your buddies. Right? So, if someone like, let's say Corey is awesome with Photoshop, let's just say, right? And he's great with Illustrator and he wants to make things at 6-point font, right? Or even lower. And then, you take photocopies of the stuff and, reduce it until you can hardly see it. And you need to have, or you use blue, green, and some other kind of colors where you have to wear your 3D glasses so you can see like, the micronized text. That's not going to fly. And the reason why is because I'm going to ask you to handwrite it. All right. So anything you're going to add to the cheat sheet, I want you to print it out, handwrite. It's got to be your handwriting. Okay. I don't want you to take your handwriting from a tablet and transpose it or anything like that. And not because I don't want you to add stuff to it, but I want it to be, it's yours and it's part of your studying, right? It's part of your ability to kind of put things together for studying. Now you don't have to do it, right? If you don't want to, if you really don't like making cheat sheets or you don't think it's a good thing or you got it, you know everything. You don't have to use it, but you need to hand in your work. I'm going to give you some scrap paper during the test like last time, and then you're going to have to put together some of the stuff, right? So today, I'm going to be introducing new stuff, but I'm going to also talk about this and run you through some examples next week, right? The test will be online, so it'll be multiple choice, some true false. That may be multiple answer. I don't know. And what it'll probably be is in the form of, here's a problem, and then you have several questions relating to that problem. Like, for example, what's the velocity? A, A, B, C, or D. What's the, what's the direction in terms of angle? A, B, C, or D, which one? Which free body diagram is the right one? A, B, C, or D, right? Those kind of things. And so that way you have, you have a selection. I'll try and not make it too many questions so you can finish it within an hour or so. Like I'm going to try and schedule it for under the time we have, because we have about just under 100 minutes, I would say, when we're in lab together. So it won't be that long. I'll try and make it nice and smooth. It will be worth 20% of your final grade, right? Just as a reminder. So 20% of your final grade, test, right? That'll be test number 2. And again, just remind you that assignment 2 is also worth 15% of your final grade. 15% for assignment 2. So it's 15, 15, 15 for all of your assignments. So it's, as an example, right? Each assignment's worth 15. The first test was worth 15. This test is worth 20, and the last test is worth 20. All right, that's how I'm evaluating you, right? So you have a chance to work with your friends and stuff, gather some information for your assignments, nice and easy, right? Then do your stuff on your own on the test, so kind of individual evaluation, and then you should have enough. I should have enough information at the end to kind of understand that you're good with game physics. Remember that this is mostly a math course, but the stuff we can do, you can add, and some physics. And you can add the ideas that we present here to any one of your games. And when you do more of a physics course with programming, when it's mostly programming and not as much math, then you'll have your foundation. That's what this whole thing's about. Any questions around the test that's upcoming for next week? Again, on Tuesday, I will do a review of the chapters that I'll be covering. And I'll be covering kinematics, right, which happened before the break. Just a little bit quickly. Yep.
You said on Tuesday you're making it like a cheat sheet available online?
If I can make it available earlier, I'd like to, right? So I can try. I mean, I have it already. I just wanted to kind of look through it, make sure there's nothing extra that might mislead you into trying to think what kind of stuff to study. It's just going to be very basic. The formulas that I've given you, I recommend you put some base cases. I'm not going to do that. I'm not going to sit there and go, here's what it is for spring. Here's what it is for this. You can do that. That's your studying, right? So if you want to put some base case, like I describe some stuff in tutorial in lab, right, about how to do, the most common cases. That's up to you to put together, like for your cheat. Yeah, well, if you want to, or if you want to put together your own examples, right? So that way you look at an example, it's like the one I'm gonna kind of post, and you have a model for it, right? As opposed to, I'm not going to do that for you, because then I'll tell you what you need to study, and exactly, and then almost like there's no need to have a test after that. So yeah, you can put your own stuff together, but I'm going to ask you to handwrite it. So no professional with Illustrator or graphic artist is going to do it for you. Okay. Any other questions around the tests? No. All right. That's yes. Go ahead.
When did you say you were making
As soon as I can. Yeah. Latest Tuesday. All right. All right. So today we're talking about energy of a system. Energy of a system. And this is, like I said, one of the most difficult areas because it assumes knowledge. And assumptions are very dangerous because we've been breezing through this stuff. Even though, we've been going one chapter at a time, I'll tell you, in another setting, we'd probably go half a chapter at a time, right? This is really quick, the way we're going. We're covering a lot of material in a very, very brisk pace. And this is good because it's a very high level overview, but it's bad because absorption might be low in some cases, right? So, please, you need to look at this material. You just can't expect that you understand and not do it. So when we talk about energy, it's almost like we're extending Newton's laws, right? And we're saying things like, what is energy actually? And back in the day, this idea of forces, and I'm not talking about Star Wars, the Force. We'll talk about that next week, maybe the week after when we see the movie, right? But we're talking about forces, as in okay, we have this energy, we know something's happening. It was almost mystical at the time. just to give you a sense of context when this stuff was being developed. They didn't understand it, the people at the time. It was like magic, pretty much. Some people knew more than others because they were scientists and engineers, but for the most part, it was intuitive. So when the scientists came along, they kind of developed this idea of energy. A couple of Newton's contemporaries, Leibniz and Bernoulli, very, very famous physicists, kind of came together to develop, this idea of energy. So this is classical mechanics, I would say, right? And we're going to talk more about this, not next week, but the week after when we come to conservation of the system, energy conservation, right? And in energy conservation, this idea, we're not talking about it today, but the thing to understand is that energy cannot be created or destroyed, right? This idea that energy stays stable in the universe, it's kind of a cool thing. So energy, though, is defined in our case as the capacity of doing work. Capacity of doing work. And we're going to talk about what work is today, mostly. So, the idea of this physical state of an object. How does it move? Where is it in space? All that kind of stuff. Energy, work, force, all related. And it's almost like, you've got this energy and you're going to perform work on a system. And when you do, energy will be transferred. This idea. All right, so if energy is the capacity to do work, right, there's two types primarily we're going to be talking about today near the end or middle to end of the lecture, which is potential energy and kinetic energy. Okay, potential energy is almost like energy that is stored. Kinetic energy is being used through motion. Okay, so this is the kind of stuff I want to talk about. And again, for game physics, we're concerned with mostly around energy that is kinetic energy. So I have a car, I'm driving along in it, and I'm building up energy because I've got some motion. And then I hit another car and I transfer the energy from my car to that car. And some of that energy gets reflected back at me, right? Because my car crunches up or whatever. And we're going to talk about that. Potential energy is something else we need to understand for gravitation, mostly for gravitation. All right, so different types of energy. There's mechanical energy, which is most of what we're talking about. Chemical energy, we're not talking about that. Thermal energy, that's kind of neat. Recently, I worked on a game where there was this whole heat mechanic thing, right? A heat mechanic. So when you fired your guns, you heated up and then you couldn't fire much more because we're making this mech game. Heat energy is also transferred by friction, right? So if you have friction on a surface, as an example, it can be heat energy is kind of generated, if you will. Nuclear energy, radiant energy from the sun and from other places, electromagnetic energy, and then electric energy, the energy that's traveling across these, charged particles. Mostly for us, it's all around mechanical energy. And again, just like it says here, mechanical energy is this combination of potential energy and kinetic energy. We'll talk about what those two things are later on. Sorry, I'll come back to that. All right, and again, I'll have these lectures available to you later today. Lecture slides. All right, so we used an analysis model before where we talked about more of, the particle model, that kind of thing, where we have, where we kind of look at a mass as a particle. We have to kind of extend that more after today, when it comes to not just looking at a particle itself, but as a system as a whole. So you've got this whole system that defines, energy in a container, if you will, right? So I've got the system, and I'm going to apply energy to the system. I'm going to transfer energy to the system. I'm going to be doing work on a system, and then, then the system is going to translate, rotate, or something that we're going to do, and that's how really we're going to use it for game. So what is a system? Like it says here, it's a small portion of the universe. I like that. Right? We don't care about the rest of the universe. All we care about is the small portion that we're working in, which is the computer game, right? And the idea that different systems could be a single object or particle, a bunch of objects, some kind of region of space in terms of a coordinate space, right? And it depends. This all may change depending on the time, the size, and the shape of the system. So a system is almost like a container. I like to think about it as a container. So imagine now we're kind of in a system. This classroom is like a system. right? And we have, it's kind of in homeostasis, if you will, right? We've got some heat energy or whatever heating it up, but we've got a certain situation in the classroom. And we can modify it. I mean, we can set it on fire if you want. That's a terrible thing to say, but I'm saying if we did, then we would actually be adding thermal energy to the system, right? Because now imagine if we couldn't. Or think about a system in terms of the Earth, right? This idea of climate change, right? Why is that happening? Because we've got thermal energy being generated by the sun's rays, right? And it enters the system, the Earth, right? And then things are allowed to enter the system, energy is allowed to enter the system, but the more CO2 and other kinds of chlorofluorocarbons that are in the air, it creates this this cloud that allows that keeps some of that energy into the system, right? This is the idea, this idea of global warming, which causes climate change, right? Which some people deny exists, right? We won't talk about who those people are, right? But you have this idea of this, and what happens is it warms up the Earth, and so the system, the Earth, is heated, and it gains energy. But the energy comes from somewhere. Remember, energy can't be created or destroyed. This idea, so it comes from the sun. The sun's rays generate energy and transfers energy from the sun to us, and it takes about, I don't know, something like 8 minutes from the sun for the sun's rays to hit the Earth, right? Traveling at a speed of 300 kilometers per second. 300,000 kilometers per second. All right. So idea that, we have to change our model is one thing. We don't just identify what's the system, what is the system that we're dealing with, but also the idea of a system boundary. So what is inside the system and what is outside the system. So I might have some kind of force coming from outside the system, and that's affecting, the conditions that are inside the system. Again, going back to that whole global warming thing, you have this idea of the sun's rays being an external force outside the system, heating the Earth, inside the system, right? Outside and inside. External forces, and there's some internal forces as well, things that happen inside of a system. All right. I think we're going to move on for that. So work, we're going to talk about work. So we know about a system. We know we have to change our model a little bit. We're talking about energy. And now, in order for us to describe energy, we're going to talk about work. And work is not like the work we do, to generate money, but actually it means something totally different. Work is done on a system. And it usually means we're exerting a force or applying some kind of influence on a system through forces, right? So an example would be if I'm moving, if I'm moving the Earth somehow. If somehow I had a powerful enough tractor beam, to move the Earth, I would be, exerting influence on the system that is the Earth, right, for it to move. And then I would have work, right? And work is all around displacement of an object. So it means that if I move an object, right, somehow I've done work on it. Okay, now this is where it becomes sometimes difficult to understand this stuff, because you're like, hold on. I'm putting energy on a system. If I apply energy, an example of this, okay, Corey's car. Okay, Corey, I'm going to use you as an example. Okay, so Corey, he's in his car, right, as an example, and try as I might, and me and his buddy, right, Terry, right, we get together and we push Corey's car. Now, Corey's car has the brakes applied, and I can't, Terry and I cannot possibly move the car. We're exerting force on the car, but the car is not moving. Therefore, there's no work. Okay, it's a different idea than, well, we're applying forces, and how much force is there? That it's not about that. It's about work is all around what have I done? If I've moved it, if I've displaced it, there's work done. If I haven't moved it or displaced it, nothing's been done in terms of work. Yes.
You're saying so a system would be like an icy lake. So on the icy lake, you have different lakes that you would on the road.
Yeah.
Like that.
That's the system. Yeah.
Yeah, and then the work would be different if it's on the ice as on the road, right?
Yeah, you could. Yeah, no, but I would be the work would be almost like affecting the system itself. So imagine if the sun's rays melting the ice, that would be work. That would be kind of influence or forces acting on a system, right? But if, or I can also say that, you know, a system is the particle as well. I can also say that, right?
Yeah, I'm trying to
So,
think in general.
yeah. So just going back to what we had before, if I have a car, that's a system. The system is the car, in this particular case, Corey's car. Harry and I are trying to push Corey's car. We're trying to influence the system, but we can't because the brakes are applied. No force, even though we're exerting force, no work has been done, right? So the idea that when you think about work, force, and then multiply by the change in the range, or in this particular case, the displacement. So force times displacement times the cosine of the angle of the force that's being applied, right, is where we calculate what work is. So what does all that mean? It means that if I push something like a system, if I put influence on a system, in this case, the system is a block, right, that I've got here, and I apply force to a system, right? So I'm trying to influence it, like we talked about before. And if I push it in a straight line, and if I actually physically move it, so I surpass the the static friction. So maybe there's some static friction that's trying to stop me. I get over it, right? I have enough force that I can surpass the static friction. I'm pushing the object, right? And then I stop. I've done some work. I've moved the object from this position here to this position here, right? I've done work because there's a change in the situation, right? Things to understand is that a force does no work on the object if the object does not move. Okay, so that's the key thing that I'm talking about here. And the other thing is that no work is done by a force on the perpendicular, as an example, to the object. So if, for example, in this case, the normal force and the gravitational force, because this thing is sitting on this surface, there's no work being done by gravitation or by the normal force because the object is not moving, right? So anything perpendicular to the object, this is kind of weird too. If you think about it, like I got the system, and anything perpendicular to the system itself, there's no work being done. It only happens when I apply force directly in line, right, or coplanar to the system itself, somehow. Yeah.
So what if how you control gravity, you just apply a lot more gravity?
Crushing the box, gravity that crushes the system. That's what you're saying. Yeah. Then, but now what we're talking about is the difference between a rigid system and a system that is not rigid. It's a totally different situation that we're talking about. I like your thinking, but it's not what we're talking about here. When we talk about work, it's almost like I want to talk about how work moves something. I want to do work to do something, right? If the box stays where it is, no work's been done, even if I crush it. Yeah.
I have a box on the box.
What?
I have a box on the box, and I'm pushing the box under.
Okay.
So there's work being done on the lower box, but not on the upper box.
Both boxes, well, because the upper box, if we're depending on the system you're applying to, if the upper box is in the frame of reference of the lower box, because it's parented to the lower box. In this case, I'm talking about like game objects, right? You got a game object, a parent, and a child game object. The child is parented there's a parent to the child as an example, right? We can think of the lower box and the upper box as one object, right? If I think about the actual upper box itself, it's inside the system. No actual work is being done inside the system. It's internal, right? But forces are being applied outside the system to move the upper box and the lower box. Now, if I consider the upper box not part of the system, then yeah, even though I'm pushing something, because I'm making the box move, the one on top, as an example, work is being applied to that one as well. Okay, I know it's a complicated answer, but it's almost like depends on how you look at it kind of answer, right? How you define it. Depends on what your problem says. All right, so again, we kind of measure displacement from the time that force is being applied, right? There's different kinds of objects we can apply it to, different kinds of system. One is a system that's rigid, right? And there's other systems that are deformable, right? In our course, because we're stretching the surface kind of very high level, we're not going to really talk too much about a deformable system, right? Like a soft body, okay, that kind of thing. And the reason why we're not talking about it is because it's more complex. Like soft body physics is more complex than, let's say, rigid body physics, right? And it's something that you have to explore a little further in your studies. All right. So again, when we think about it, we look at the normal force and the force of gravity, and they kind of cancel out because they're perpendicular forces to the coplanar force we're using to move an object, right? So I'm moving an object in the direction of this arrow here, right? And you notice that I'm moving it in a specific direction, right? And I have a change in range, or a change in, there's a displacement that's happening from here to somewhere else. Here's the angle of the work being done, the force that I'm exerting, right? So the angle's up, right, at some angle to the perpendicular to the plane, and if it was something like 90 degrees, this is why there's no work being done on the perpendicular, right? Cos of 90 degrees is equal to 0. Remember that we multiply to figure out what work is. We have to take the force multiplied by the displacement, cos theta, right? And if cos theta is equal to 0, then we're going to have 0 work. So anything on the perpendicular up and down to the plane that we're applying the force, right? There's no work being done there. All right. Work is a scalar quantity, so it's not a vector, right? Even though work has a direction, we're pushing it, we're actually displacing something, right? We can express the, direction we're going in, but work itself is a scalar. Work is a scalar, and the unit for work is the joule, right? So joules. And a joule is equal to 1 Newton. Remember we talked about Bernoulli and all this kind of stuff. This work has been extended from Newton, right? So a joule is 1 Newton. 1 Newton meter is what it is, right? 1 Newton meter. So basically, notice I'm using force over distance. And if you think about that, what that is, that's what work is. Force over a distance. If I apply my force continuously over a distance, I have some kind of work. If there's no distance, there's no work. Okay? And again, you could also express it as in kilograms per meter squared over, second squared. All right. So we transfer energy. We have this idea of energy transfer. I transfer energy from an external source to the system, right? The system can translate, displace. I displace the entire system, right? And when I do so, work is being done, okay? So even though energy, work, and force, they're all kind of related, work means something different. Energy transfer is one thing. Work, when we talk about work of a system, we talk about movement, right? And when work is done in a system, positive energy is being transferred to it, and when the work is negative, right, energy is being transferred away from the system. Okay, so the idea is, how do I have negative? How do I have work that's negative, right? Well, what's happening is I'm either moving it back. Remember, displacement is all around where you start from. So the initial position versus the final position. And if I move the system back to where it started, I'm actually doing something called negative work, but there's no negative work, right? So what I'm actually doing is removing energy from a system. I've displaced it and I take it back, right? But again, it all comes down to your point of reference. Because if I move a system, an object, let's say a certain distance, and then I leave and come back and I push it back, I can also express it as work is being done again, but the total work done from the beginning is 0. All right, just a reminder, when we have, we may deal with some vector stuff in this section, and I wanted to include this, also included in your book as a review, right, where the idea of dot product is really a projection of one vector onto another vector. So an example would be this. You have a vector A in a particular direction, and you have a vector B. And the dot product of A, B, right, what it does is it actually projects B down onto A, right? And that's what the dot product does. And you can also think about it as AB cos theta. That's what we're really doing. We're translating one vector onto another. So if B was the vector that describes the force, and A is the, kind of describes the direction that we're pushing, right, in general. The projection of B onto A is the dot product between the two vectors, okay? And again, when we talk about work, again, it's the force, times the change in the distance or displacement, if you will, cos theta, or in other ways, we can express it as the force dot, the displacement, right? So force is maybe a specific angle, and then we're going to use the dot product of that and the displacement, the total displacement vector, right, as an example, to get a projection of the force onto the displacement vector, all right? Now, why do we care about that? As an example, because once we talk about vectors, it becomes a little easier to calculate some stuff, especially when it comes to computer graphics, right? We use dot product to express things like, we just define a shader, like a diffuse shader. We use dot product, right? N dot L, if you guys remember that kind of formula for diffuse, creating a diffuse shader. And we'll talk about more of that when it comes to, in your computer graphics course, you should be learning more about that. So I just want to briefly mention that. Power. Okay, so we talked about work. What the heck is power, right? We're going to talk more about power in the next section, but I wanted to bring it up early because I want you to get an idea of what power is. So we talked about work being done over distance. Work is energy, force being expressed over a distance. We're kind of, influencing a system to move a certain distance. That's work, right? Well, power then is how much work we can do over time, right? How much work we can do over time. So, and usually it's expressed in joules per second or watts, okay? How much work we can do over time, and we express it in watts. Now that watt must be some kind of, it must ring a bell for you, watts, right? Because we usually talk about, when we talk about watts, we talk about real, like electricity, right? Volts and amps and watts and all kinds of other stuff. What the hell are those things, right? Well, and how can we relate watts to work, right? Because what are we doing when we talked about work? We're moving a system, right? The system can be, and we're talking about energy. In our case, we're mostly talking about mechanical energy, moving things around or, changing their angle or that kind of stuff, right? But there's other kinds of energy we talked about, like, for example, electrical energy. And you can apply work to electrical energy in terms of how much flow you have, right, from one place to the next, one position to the next. How much energy flow do you have? And that is work over time. All right, so power. All right, work done by a varying force is also confusing. So we talk about work, right? Here's work. We're going to force over, over distance. That's what work is, right? But now we're talking about what if the force is varying? And a great example of varying force is a spring, okay, where we have some force, as an example that we apply to a spring, we compress it or, stretch it. And once we apply this force to the spring, we're doing work because we're moving a spring and, we're compressing or stretching a string as an example. And then, the work that's being done on an object that's connected to the spring varies over time, right? Because of this idea of elasticity, right? Where a spring kind of deforms and comes back to normal, right? Or there's a kind of a restorative force that comes into play, right? Now, this should be familiar to you when you look at this graph, because it looks like, to me, area under the curve. And when I talk about area under the curve, I'm talking about integrals, okay? So remember we talked about calculus and, we talked integrals. And I know people hate integrals in calculus, but we got to talk about it again, because to understand what's happening here, this area under the curve, this is the amount of force being exerted over a distance. Again, here's your initial position here, and here's your final position, x initial and x final. And then we have some change in the, kind of the distance. And this change over a particular time frame, as an example, distance over time is, we can say it's speed, right? Or velocity, depending if it's got a direction. We talk about it as velocity, right? And we can calculate, we can determine velocity, right? from things like acceleration with integrals, right? And we can also determine velocity from position, from, you know, with calculus, with differentials. All right. So this idea of area under the curve, how much work we're doing because we're exerting force over distance. And really, even if the work that's being done is varying, it's not equal all the way. It's not a triangle or some kind of rectangular shape that we're doing. It's not, you know, constant. It's kind of going up and down depending on we're applying more force and less force. Then we can derive this idea of, the integral of, if we want to find, the total forces that are being applied, or the work, is really the integral of your initial position, the fixed integral or the known integral from your initial position to the final position of the total force across the x-axis. All right, in this particular case. Now, if you didn't do well in calculus, right? In the calculus section, you're going to go, oh damn, I'm going to take a spoon to my eye and take my eyes out. I don't know, because this is bad, right? You hate integrals, right? Please don't do that. Don't mutilate yourself. This is a good thing, right? Because you should kind of recall what this is all around, right? It's about, hey, I'm moving an object and I want to find the total area, which is kind of the total displacement over time, right? Over distance. How do I do that? I take the integral of it. So it's good to know where it comes from. And think about this as when we use the ext or ext subscript, we really talk about work done from an external force, all right? Or some kind of external agent, like they call it. An external agent that's applying force. And we want to find the net force that's being applied to a system. We look at all the forces, right? Again, the area under the curve. And what we can do is, if you look at the second equation here, this is the base case, but this is what we really want to look at. The sum of all work that's being done in a system is the work that's being exerted on a system by an external agent, which is equal to the interval of the initial position all the way to the final position, right, of the sum of all forces on the x-axis. Okay, that's what it is. So it's really looks complicated, but if you think about what we're just doing, we're just describing what I've been talking about with math, right? That's all I'm doing, right? As opposed to, well, forces can vary across a distance. And they talk more about this here. I'm just going to go into the spring example here. So, the idea that you have, this motion that's happening. Notice that there's 3 steps here, all right, where the spring is being stretched. I'm just going to zoom in there so you can see it a little bit more. We're going to talk about this a little bit more detail as we go forward, because I want you to kind of understand how this works. So I'm stretching a spring, right? And notice that the force that's being exerted, the spring force, is being exerted away from the direction that I'm applying the work. So I start at this position. This is the neutral position. And I use some work on this block, right? And I'm expressing this thing as in I'm pulling the block a certain distance, right? But there's force being exerted to fight me, which is the spring force that's fighting me to restore the spring to its original shape. And it's going in the opposite direction to what I'm trying to apply force. So again, I'm an external agent applying force to a system, and I'm moving the system in a certain direction, but the spring is fighting me and pulling back, right? That's what's happening. That's this case. In this case, there's some kind of displacement, which means work has been done, right? Here, in this case B, there's no work that's been done in this particular case because the spring is at rest, right? I have not applied any force. The object or system hasn't moved any distance, and therefore no work has been done, right? And this is another case, the third case. I'm compressing the spring. So now I'm pushing the spring as much as I can, but the spring is pushing back, right? Because it's trying to, this restorative force of the spring is trying to push me back so that the spring, returns to its original position, its original shape, right? Spring force, this idea of that, right? And so that we have forces that are pushing back at my external force, right? Resistant forces, if you will. And this motion, this oscillating motion, if I pull an object, right, and let the spring take hold, we're going to talk about that with Hooke's law in a second, right? What happens is we have this force in oscillation, right? It oscillates. right? At a specific frequency, actually, right? And what ends up happening is that eventually the spring goes back to equilibrium because it reforms to where it originally started. And then at that particular moment in time, that instantaneous time, right, there's no work being done. The work is being done as the spring is moving around back and forth. It's being displaced. When it stops moving, no work is being done anymore. A really great example of understanding how what work is all about, right? Again, it could be, how do I describe this motion? Calculus. Because area under the curve. We have a varying force that's being applied to the block. The spring is applying that force back and forth, right? It's not a constant force, right? If it was a constant force, then it wouldn't be a spring motion. It'd be something else. And in our first assignment number 1, where we had Spider-Man being pulled up and, kind of down from the ceiling, right? He was hanging from a web, and he kept on going back and forth forever. That's not realistic because there's nothing to stop him. All right, there's nothing to stop him. Gravity's not stopping. He's not slowing down. He's just going forever. Here, the spring will eventually, the natural order of things is for things to spring back, if you will, to their natural form. So too in the case of our personalities. Someone who is the way they are. It's kind of really weird how physics and metaphysics kind of tie in together, right? A person can be the same way. If you try, they can stretch and try and be somebody else. It's kind of an analogy. Maybe it's a bad one. And then they stretch, they kind of spring back to where they are. And sometimes catastrophically so. And we see some of that in our society. All right, so let's think about this. I know that's kind of like a little bit of an aside, but please forgive me. I've got this idea that we wanted to talk about, and this other thing that describes the motion with springs and it's usually called Hooke's law. Hooke's law is, again, this force of a spring is negative kx. And what is k and what is x? X is the position of the block at rest. So if I was here, right, that is the original x position in equilibrium, if you will, right? K is the spring constant or the force constant that it's really all around stiffness. How stiff is that spring, right? So it multiplies by the total distance, right? And we get this idea of the force of the spring at any particular point in time. So the stiffer the string is, the more force is exerted as we move away from equilibrium, right? So if I have a spring in equilibrium at a particular point in time and I move that spring, I pull it in a particular direction, as an example, there's force being exerted fighting me to get back to equilibrium. Okay, this is the idea. And it's the stiffness of the spring that's allowing that to happen. Now, there's going to be a certain time where I exceed the total tension on a spring, and I can break the spring, right? But springs are one of the mechanisms we use in mechanical engineering, so that we can use things like to open things, close things, to resist things. We use it all the time in our cars. We have springs in our cars that give us a cushioning effect as we drive, and all kinds of other things. So again, a key formula we'd say which is the force of a spring is equal to negative kx, right? And here they just describe it a little bit more with vectors, okay? I'm going to keep moving. All right, so we also talk about this work done by a spring, which is the interval between the negative x max. So that means that depending on where I move it, I take that, the object on the x coordinate, right? And I take the interval of that from a negative x max to 0. So from the place that I've displaced it to 0, how much work is being done, as an example, and then of negative kx delta x. Okay, that's what the interval is. The integral, sorry. And the integral is, when you look at that after you do some calculations, you realize that when we talk about the work of a spring, it's actually equal to 1/2 kx squared. Okay, and that's the real equation. So when I put it on your next test, when we talk about the next thing we're going to be testing on, this stuff that we're talking about now is going to be on your final test, right? Which will happen not now, but towards at the end of the semester, which is in January, right? And this is one of the equations that are going to be on there. So work of a spring is equal to 1/2 kx squared, right? And it says kx squared max because that's the maximum position that you can move, or whether you stretch or compress the spring, right? And whatever that is, right, as an example, that's going to be the work that's being expressed. And it says here that the net work done as the block moves from kx max to negative x max to x max, right? From compression to contraction is 0 because it comes back to normal, right? It normalizes back to the origin. And I think I want to move on from there because we're going to talk more about this stuff later on. And it also talks about here, again, I'm not going to go too crazy. You can read some of this yourself as well. But the idea that if I have some kind of force that I'm applying to a system and I'm using a spring to apply work to a system, how does that work, right? I have some work that I'm applying and I have some initial position and a final position that the block will move to. Because let's say, for example, I'm using a block to compress a spring. And if I look at the block, not the spring as a system, but the block as a system, and what happens because of the spring force that happens, I can look at the initial position on the x-axis and the final position of the x-axis. And really, after you do your integration, you get to this notion of the total work applied, from the spring is 1/2 kx squared minus final minus 1/2 kx squared initial. So basically the initial position relative to the spring where it started and the final position. It becomes almost like an average, average work, which is kind of what we're trying to figure out. We're trying to figure out how to define varying work over time. Yeah. Yes.
Oh, I was just wondering. So like this kind of confused. What is it for something common for like?
So I'm still using external force to displace the spring, right? Yeah. When I've done that, if I stop there and let it go, there's a force that's pulling back at me, right? And that force that's pulling back at me is the spring force, right? But I've actually done work because I've actually moved an object, right? Or moved the spring. I've displaced the spring a certain distance. Remember, force over distance means work, right? When I let it go, it's going to also, there's work going to be still done on it until it returns to equilibrium. And once it returns to equilibrium, there's no work being done, right? Because it's not moving anymore. All right, so that's really enough about springs. Is there any questions around springs? I kind of went over it quickly, but the idea that there's varying work over distance, which means the power varies. Power is some kind of work that's being done over time, okay? So think about this now. We have the idea of two types of energies. And again, I'm probably going to take a short break soon because I don't want to go too much over with this stuff, right? I got two basic energies we want to talk about here when it comes to game physics, right? For sure. One of them is potential energy, and this other energy is kinetic energy, right? And the reason why we care about kinetic energy is because of collision response, okay? For sure, we can detect a collision, right? But what do we do when there's energy that's being applied to an object that's colliding with another object? What happens, right? And how do I express that so it looks natural in a game, right? It doesn't look weird, right? Like you ever see a block that, a ball that, falls and then it doesn't bounce? It just kind of, boom, it just kind of sits there, right? It doesn't look too natural. It kind of looks weird, right? You expect even a ball or even a block to kind of bounce a little bit. Depending on the elasticity of the surface it falls on and the elasticity of the object itself, right? A ball is very elastic. It's made to kind of squash and stretch. This reminds me of the 12 principles of animation, but, squash and stretch. A ball squashes and stretches, but the volume stays more or less the same. And then what happens is that spring force from a ball projects it upward again. It reflects from the collision all the way up. And what's happening is this kinetic energy that's deforming the ball like a spring is being used to transfer the energy from the ball to the spring. The spring is being deformed, which is the ball. Think about the ball as like this little spring. It's deforming the ball to its maximum compression. And then what's happening is the ball is going back or reforming back to its, restoring itself back to its normal shape, right? Like a spring, the ball is going to come back and the energy is going to be reflected from the area that it hit, some form of it, some amount of it, back into the ball. Depending on the angle it hits, it's going to lose energy, right? It's not going to go quite as high because remember, we're going to apply energy not just in the horizontal or not just in the vertical unless I drop a ball directly from overhead straight down, right? But also to the horizontal. And once I've transferred some energy to the horizontal, the ball isn't going to go as high because I've transferred energy. There's two components, horizontal and vertical, right? Now, if I drop a ball directly ahead, for the most part, there's no horizontal energy, so it's going to kind of bounce up. But what's bringing it down is gravity. Gravity is always pulling that system back down. It's applying, potential energy is being transferred to kinetic energy, and there's energy that seems to be lost. But what's happening is there's work that's being done or a force that's being exerted on the system to stop it from bouncing. Phew, right? Balls are, you might think of a ball example is really easy, but actually, if you think about what's happening with compression and so on in stretching, the ball is like a spring. But we can express kinetic energy, this idea of force or work that's being done with motion. Kinetic energy is mass, right? I'm moving mass with some speed, right? That's why if you look at what the formula is, I've got my mass and I've got some kind of speed, and I'm moving a mass with speed. That kind of determines the amount of kinetic energy I have. All right, mass with speed. It's not displacement. Okay, it's not velocity, right? So in this particular case, K is the kinetic energy, M is the mass of the particle, and V is the speed of the particle. And whenever we want to find kinetic energy, we say that K is equal to 1/2 mv squared. And that seems very, very, it does not remind us of something. We looked at other things last week, which was, hey, centripetal force, is mv squared over r, right? It's always like v squared over something. It's something to do with some kind of motion, speed, if you will, right? So we want to find, when we talk about kinetic energy, we're talking about motion again. Kinetic, or kinesis from the Greek word, is really around movement, kinesis. And when we look at the formulas again, and I want to find, if I look how we derive it, we start off calculating our work when we're using the math to say that we have some work that's being done by an external agent, right, on the system. So here I've got this block, right? And it's the sum of all forces. It's the integral from the initial position to the final position of the sum of all forces that are being applied to an object, right? And when we transfer it, remember, we can also say that because this is the sum of all forces, the sum of all forces is like, saying mass times acceleration. We can say that, well, it's like the integral of the initial position to the final position of mass times acceleration, right? And as they kind of continue deriving from acceleration, they kind of go back and integrate into velocity. Notice that it moves from acceleration to velocity. We can kind of come to the form where when we have an external force being applied or external work that's being done in a system, we can say that 1/2 mv squared final minus 1/2 mv squared initial is the total work being done in a system, like we talked about earlier, right? And we can also express it in terms of the kinetic energy final minus the kinetic energy initial is equal to the total, or the difference in kinetic energy, right? What does that mean? Why am I telling you this stuff? Well, it means that we take a look at the motion that's being applied to the mass, right? I've got mass that's moving, right? Spaceship, mass that's moving, right? And I look at that thing, and there's some kind of kinetic energy that's being involved to move that mass, right? And when I want to express the work that's being done, right, how much kinetic energy is in the system and the work that's being done, I can look at the total kinetic energy at the end and the total kinetic energy in the beginning, and that I can kind of decide on how much work is being done. So you can kind of relate work to kinetic energy, all right? There's energy, and that's how it kind of relates back to work. Okay, so again, you can see that there's some velocity initial and there's velocity final. We have this delta x, which is the change in position, as an example, and the sum of all forces to push this mass, right, with some kind of velocity from one position to the other. So this is something we're going to cover more when we talk about conservation of energy, but I want you to think about this now. I have this idea of energy initial plus work, some kind of work, right? I'm applying some work to an energy source, right? Is equal to energy final, right? This is a kind of a key equation. I've got some energy, right? and I apply more work to it, right? As an example, I'm driving at a certain, or I'm doing something with my, let's say, kinetic energy, right? I'm moving a mass over some kind of speed, and then I do some work on the mass, right? Which means maybe I accelerate it. I move it faster, right? As an example, and that's going to be equal to my final kinetic energy. And if I apply kinetic energy to it, right, some kind of extra work, because work external is also equal to kinetic energy, then I can have a total at the end. And here's another one which we're going to use the next time, which is kinetic energy plus potential energy, which we're going to talk about later on. So kinetic energy is expressed in K. Potential energy is expressed with the letter U, which we're going to talk about in a second, right? Plus some kind of work. So kinetic energy initial plus potential energy initial plus some kind of work, right, is equal to kinetic energy final plus potential energy final. And this is the idea of when they took this formula for the next time we talk about conservation of energy. And they said, hey, you know what? Energy can't be created or destroyed, because if I take my kinetic energy initial, potential energy initial, and work, right? Whatever initial energy I had is going to equal to the energy at the end somehow. Okay. So this idea of the work kinetic energy theorem is what we're talking about, how we can relate work to kinetic energy. This idea of that, yes, we move. Remember, work is also about force over distance. I got some force, I'm displacing it, I'm using force, I'm applying force to a system over some kind of distance. Okay? Force and distance. Displacement, if you will. And then I got this other notion that I'm taking a mass and I'm moving it at a certain speed, right? So kinetic energy is mass with speed. I've got some kind of car that's moving, right? And work is force that I'm applying over distance. Someone's dying over here. I know it's tough to look at this stuff. It's hard to look at slides and talk about this stuff, but I gotta discuss the concepts, and then in tutorial we'll have some examples. So this idea that they're related, that's what this slide really means. And here's one. The net work that's being done in a system is equal to the change in kinetic energy times, which is equal to the kinetic energy final minus the kinetic energy initial. Again, we're saying the same thing over and over again. Here's an example. What is the net work required to accelerate a 3 kilogram object, from 2 millimeters per second to 4 meters per second? Okay. So I'm talking about acceleration. How do I figure that out, right? Well, it's kinetic energy. Kinetic energy is mass, times velocity squared, really, at the end of the day, mv squared, right? This idea of that, right? And if that's what kinetic energy is, I've got my mass, 3 kilograms. I've got my velocity initial, my velocity final, right? And then I can equate it back to the net work that's being done, right? So there's some kind of a final velocity, 4 meters per second, times mass, right? So mass would be 3 kilograms times 4, right? So that's 12, right? Minus the kinetic energy initial, which is 3 kilograms times 2. So 12 minus 6, in this particular case, is 6 joules of work that's being exerted, right? Because it's how many kilogram meters, or Newton meters, if you will, that are being exerted, all right? And that's what work is all about. And that's why we kind of relate work to kinetic energy. And if that's the case, some of our kinematic equations that we've used that have been derived from this stuff, actually, or they can come back to, they've been integrated from this stuff, can go back the other way. And sometimes you can solve an equation in many ways. One way is using this whole idea of potential energy and work. And the other way you can use just kinematic equations. And you might have a third way using trigonometry to figure out a system. Okay, so however you figure it out on a test, it doesn't matter. It's just giving you more tools to understand how to apply motion to a system. Having a great impact, I can say, right?
It's not me.
It's not you today. All right. So we talked about kinetic energy, but what the heck is potential energy? All right. So for this one, I want you to imagine I'm holding up some kind of object, right, off the ground. So I'm going to have an object. I'm holding it in my hands, and I hold it off the ground. Inherently, that object that I'm holding off the ground you can think of it as having potential energy. I've got this thing in my hand, and I'm holding it above the ground a certain distance, right? And what's that potential energy, right? It means that if I let the object go, my potential energy is going to transfer into kinetic energy, right? And it's going to tumble towards the ground. Where's the energy coming from? The work that's being exerted from the gravitational forces, right? As I lift an object higher and higher off the ground, so too does the potential energy rise. Potential energy then is a ratio of how high it is off the ground, because the higher it is off the ground, the more potential energy is going to be transferred to kinetic energy when potentially I let it go, right? And for us, mostly for us, it's all around gravitation that we care about, because the higher up we send an object, you know, we're going to in some way store some kind of energy inside that object, right? Because I'm kind of putting it off the ground. An example of this would be a roller coaster. I pull a roller coaster at the top of the ramp, and then I let it go, right? And then as it moves down, it has a lot of potential energy at the top, and the potential energy is slowly transferred from potential energy to kinetic energy as it moves down. All right, this idea, right? So this energy transfer again, conservation of energy, which we're going to talk about later on, not today, right? Is energy being transferred from one state to another state, from a standstill to movement, and then eventually again to a standstill. So some kind of equilibrium. So potential energy. And like we talked about, the ones for us is this idea of gravitational forces or gravitational potential energy, right? Oh yeah, he's dying. Dying. Right? I don't know what to do. I'm trying to set it up to make him more interested. But so I got this idea of this physics book. So you got this physics book. Here's an example of potential energy, right? And as I lift it higher up, what ends up happening is I gain potential energy, because I actually, it's almost like saying in your mind, I increase the potential energy. You know what? I always think about potential energy as something like this. If you take, a glass of water, right? I always think about like this, especially at home, right? You fill a glass full of water and you give it to a kid, right? That's a lot of potential energy, right? Because that kid can take that glass, whip it at your TV screen, right? Or just plainly just knock it off the table. Lots of potential energy, right? But if I put that glass on the floor, there's less potential energy, because even if he knocks it over, it's not traveling a great distance, right? Higher up, worse than putting it down on the ground, right? And so I always thought about that when I learned it back when I learned this stuff in high school. So again, when we talk about this change in vertical displacement, the higher it is up, as an example, the more energy that's being kind of expressed, right? So we can say that the book, we take, mass times gravity, so the mass of an object, right? Because remember, we talked about mass mv squared, right, as kinetic energy, right? Kinetic energy is 1/2 mv squared, right? Well, here, what we're doing is we're taking mass times gravity, right? Mass times gravity, which is kind of an acceleration, that's what it is. And we take the final position, right, minus the initial position. And that's how we're getting the total potential energy that we're storing. And again, you can see that we have external forces, in this particular case, gravitational potential energy, right, which is also expressed in terms of U. So UG, is the gravitational potential energy, right? And we can express it in terms of how high up it travels compared to the initial position. So if initial position, if we look at the base position as the ground, which is kind of a good thing to do, and if we raise an object up, it's easy for us to have some kind of distance traveled. So the height or displacement of the object from the ground is the total amount of potential energy. And there you go. UG is equal to mass times gravity in the y, right? So how much I move it up compared to where it's at, or the difference, if you will, the delta, the work exerted is the change in the potential energy. Okay. Again, we want to think about potential energy as a scalar, right? Because it's expressed in joules, so Newton meters, the same way as kinetic energy is expressed. Okay. We kind of talked about that being a reference. Okay, how about elastic potential energy? So we've got this idea of potential energy for gravitation, gravitational potential energy, but we can also express springs as elastic potential energy, right? What does that mean? If I coil up a spring, if I compress a spring, right, and I keep it compressed, it has elastic potential energy, right? So another way of thinking about springs, right? So I've got this energy that I've generated, a potential energy that I've generated by compressing a spring. And then when I let the spring go, it's going to change from potential energy to kinetic energy, right? As it reforms, it goes back to normal shape. I know I'm kind of beating a dead horse here, right? But I'm trying to tell you this so you have enough examples so you get the idea of what's happening. Any questions so far? I know there's a lot of stuff we're looking at, and there's some formulas, but remember the good things, right? We're going to get the formulas. We're going to look at some examples in lab, right? And you'll be able to work through some of these ideas. Here, I'm just talking about concepts, right? But in lab, you'll be able to look at some of the practical applications. All of this stuff, by the way, is good for game. All of it. Spring action, all that kind of stuff. Anything like that. For example, like I said, we talked about balls, bouncing, all that stuff is all the things you can apply these formulas to. Now, here's something interesting. We talked about the potential energy. So US, right, of a spring, right, US, is equal to 1/2 kx squared. Why is that? Because we know from Hooke's law, right, that that's the case. We want to be able to have the total energy or work that's being done is 1/2 kx squared, right? And what they've done here is very interesting. They've done kind of an analysis where they say there's 3 states, right? We want to talk about this little graph, right? And they talk about the graph being this energy bar, right, from 100% to 50%. Okay, and let's take a look at this here. So where you have the idea that in A, the spring is in relaxed state. So it's in equilibrium. And they use the spring for this example, right? Notice that the kinetic energy is 0. The potential energy is 0. In fact, the total energy of the system is 0 because there's nothing going on. Spring is in a relaxed state. Okay? And that's A in this first example. Then in B, I compress the spring. So B and C, the hand, that's the external agent that's working on the system, right, is compressing the spring. Notice that the potential energy, what's happened to potential energy, right? As I compress, I'm just going to move up here so you can see it. As I compress, the potential energy rises and the total energy of the system also rises because I'm exerting force, influencing the system, right? I'm increasing the potential energy as I push the spring, right? That's what's happening. So the energy levels rise, right? And then as it reaches the maximum compression rate for the spring, right? Notice that it goes from some energy level to the maximum energy that it can hold. This maximum energy, because I pushed it to max. I've compressed it as much as I can, right? So my total energy in the system is 100% in this particular case. Then, right, I let the spring go. And you can see that the potential energy drops, but my kinetic energy increases. I transfer energy from the potential energy to the kinetic energy. But the total energy itself remains the same, right? Total energy of the system, that I've imparted energy, I've influenced the system, and the total energy remains the same. It's just transferring from potential energy to kinetic energy, right? And then what happens is eventually it gets to the maximum kinetic energy for the system itself, the maximum amount of energy that the spring can give us, right, to impart. And so the total energy becomes 100%. Eventually, though, the energy, because of frictional forces and so on, will reduce until there's no more energy left in the system because the energy has been absorbed by the frictional forces that are being applied to the system to slow it down and stop it. Doesn't matter whether it's on a surface or inside of a fluid like the air, right? It'll eventually stop. But the energy is maintained. The energy is not destroyed. It's just transferred. So this is a really cool concept. I like it. And the idea of energy transfer, right? And it's easy for us to understand that. Okay, so we talked about, this external forces, but there's also internal energy. So we talked about kinetic energy, and I'm only going to really talk briefly about this because it doesn't really pertain to us so much with game, right? But think about this in terms of heat transfer, right? If I take a book and I rub it against an abrasive surface, right? The frictional forces will cause thermal energy to rise, internal energy to the system, right? So over time, I start off with kinetic energy instead of potential energy, right? And I transfer kinetic energy into internal or thermal energy, but the total energy of the system remains the same. Very interesting. Not applicable to us, but interesting. And the two forces we're going to be talking about the next time we're passing this lesson. Let's say we stop this lesson. We talk about the next part is going to be conservation of energy, right? So today it's almost like an intro to what energy, work, and power is all around, right? And the next time we talk, next lecture, not next week, but the week after we've done our test, right? We're going to be talking about conservation of energy, right? And the two conservative forces are gravity and spring force, right? Because what ends up happening, the reason why the conservative is because energy is transferred from potential energy to kinetic energy, right? But the whole energy of the system itself, it stays the same, okay? In fact, it balances to zero. Okay, I'm not going to talk too much about this because we're going to talk more about it the next time, this idea of conservative forces. And there's also non-conservative forces, right? And the idea that mechanical forces is the total of, example, kinetic energy plus potential energy, right? And the reason why they're non-conservative is because energy is being lost, if you will, or absorbed somewhere else, right? Okay, so I don't want to go too much into detail. I know I've kind of, killed you guys with some of this stuff. I just want to make sure that we've got it for the most part. I think we've got most of the stuff I want to talk about. But when it comes to conservative force, the idea that if I have the total force I'm expressing across the x-axis is equal to the change in potential energy over the change in, kind of distance. All right, so delta U over delta X. So how much potential energy has changed over a particular distance? Okay, and again, I'm not going to go too much detail about this because it doesn't really pertain to us too much at this particular time, right? So it's here in your book. You can totally look at it. They also talk about energy diagrams and equilibrium and how you express those things. Again, not something that I'm going to delve very much into, but it's in your book to look at. So that's it for today in terms of lecture. We're going to move towards the lab after this, and we're going to talk about more examples. In your examples, I've got some really cool examples about each type of, each of the cases that we're talking about. And these are the most common examples that we're going to be talking about again. And every time you look at a PowerPoint that I've given you, it's always talking about the most common examples that you might see on a test or on an assignment. Okay? Most common. Any questions around this stuff? All right, that's it for lecture today. So we'll be meeting in lab at 5:30 for today. And again, just a reminder, passing, just for people who are here for lab, just a reminder that, one more time, that the test is next week on both Tuesday and Thursday during lab time, during your regular lab time. And on Tuesday during lecture time, we're going to be doing a review. Yes, that's a question. The test format will be multiple choice true false, and I'll give it mostly would be pertaining to one problem. You might have a bunch of questions around one problem.
Starting kinematics and everything else.
Yeah, from kinematics to what we talked about last week, not including this stuff. Yeah.
Yeah, that's my question. What's going to be?
So it'll be like, I think it's chapter 4, 5, 6, and 7 in the book. Okay. Any questions? All right. I'll see you guys in lab.